Alright, good morning, good afternoon, or good evening, class, depending on when you decide to watch this video. This is Mr. Arosena, and today we are talking about momentum and impulse, because yesterday we reviewed Newton's laws of motion very briefly, and we spent most of the time talking about how to find what direction the net force is going in, because that's important, especially for later on in this class. Alright, today we're going to review momentum and impulse because we've already done this in Physics 11, so we'll just do a quick review of what momentum and impulse are, and then go through some examples of it. Alright, so momentum, as defined by Newton, he referred to momentum as the quantity of motion. And some textbooks will refer to this quantity of motion or refer to momentum as a measure of an object's inertia. So it's sort of like just how much movement the object has. Okay. Now, when you think about this with examples from your own life, things with lots of momentum tend to either be very heavy or very massive, or they move very fast, or they do both. They're both very massive and very heavy. Sorry, very fast. So, for example, like talking about, say, like a vehicle, a large truck would have moving at say 50 kilometers an hour has quite a lot of momentum. And if you were to compare that to say a compact car traveling at the same speed, the truck would have more momentum because it's just more massive. Okay? So momentum is sort of a combination of both mass and velocity. Now, if you remember from Physics 11, this is the equation that we use to calculate momentum. Momentum is just the product of mass and velocity. Momentum being a product of velocity, or having velocity as part of its calculation, means that momentum is a vector, and therefore momentum has direction. Okay? You can describe momentum without direction, but it doesn't make much sense other than just deciding just how big it is. Momentum generally always has a direction, so it's a vector quantity. Okay? Right, now, when Newton described momentum, he also coined the term impulse. Now, in our definition, impulse is the change in an object's momentum. And it's defined as follows. So the impulse is defined as the amount of force applied over some amount of time. So the product of force and time. Okay, this is a variation of how Newton wrote his original second law. Originally, Newton wrote his law as this, as the amount of force needed to change an object's momentum given some amount of time. So if you wanted your object to stop faster, you would need to use more force, because more force means the amount of time needed to change the momentum decreases. If you wanted to take more time to stop your object, or you used less force, the amount of time needed to change the momentum would be a lot smaller. Now, this sort of makes sense because if you want to stop something very, very quickly, you tend to use a large amount of force. If you use a small amount of force, the object's momentum or the object's velocity tends to change fairly slowly. Consider, what's a good example of this? I guess consider a collision, a car running into a wall. If the wall exerts enough force, it'll stop the car very, very quickly. If the wall does not exert enough force, then it doesn't stop the car and the car keeps going. Okay? Other examples of this include things like, I guess, well, actually we'll go through the example. Go through an example in a moment. And we'll give you an illustration as to large and small forces. Alright, so for those of you who took my class last semester, you'll know this example already. For those of you who did not, then this example will be new. So let's look at this example. Alright, so this is a scene from an old Spider-Man comic book. And here, the Green Goblin had kidnapped Spider-Man's girlfriend, Gwen Stacy, and had thrown her off this bridge. Okay, there's Spider-Man. Spider-Man's up here. Okay, he's upset. Gwen, no. Alright, so Spider-Man realizes, okay, I've got to catch her, stop her fall before she hits the water, because it's quite a ways. That bridge is quite tall. Okay, so Spider-Man's got her, throws his web line out, catches him. Oh, I should erase this. Erase all the ink. There we go. Alright, there, Spider-Man catches her. He did it. Loves his spider powers. Okay, big problem. Okay, Spider-Man gloating, kind of patting himself on the back. Realizes something's wrong. Something's wrong. Oh, apparently Gwen died still. Alright, explanation. Well, while he's doing this, Green Goblin's here saying, "Romantic idiot, she was dead before your webbing reached her. Fall from that height would kill anyone before they struck the ground." That's actually not what happened, but whatever. Goblin's kind of crazy. Alright, for you, my friend, death will come more quickly and more surely than the shock of a sudden fall. And then Spider-Man gets all crazy and beats up the Goblin after this. Anyway, so what actually killed Gwen? Was it the fall or something else? Okay, question. When I did the analysis before, we assumed that the height she's fallen before Spider-Man catches her is approximately about 90 meters. And now, as she's falling, we know that her acceleration, because she's falling, is negative 9.8 meters per second squared. I should actually make this height negative, okay, because she's falling from being thrown. Okay. We'll assume that the Goblin is not throwing her off too far, so she'll have some and no initial velocity. And the key here is we want to figure out just how fast is Gwen falling just before Spider-Man catches her. As she's falling, she's going to gain some velocity. Now, looking back at our kinematics equations from last chapter, we can use the following equation. V final squared equals V initial squared plus 2AD. Now, initial velocity is 0, so this doesn't matter. So we can just simplify this equation to be V final squared equals the square root of 2 times A times D, which when you put in the numbers will look like this. 2 times negative 9.8 times negative 90. Now I can sort of see why the height is negative 90, because otherwise the math would not work out. And when we calculate this, I'll pull up my calculator. Okay, so when we calculate this, we get the following. Oops. 2 times 9.8 times 90 number, we'll square root that. So she's falling at a rate of about 42 meters per second. Alright, that's how fast she's going. Now, when Spider-Man catches her and stops her, the stop is pretty instantaneous. Okay. So let's say that she stops with a time of, I don't know, let's be generous. Let's say 0.2 seconds. That's how much time it takes Spider-Man to stop her fall. Okay, now using Newton's second law in its original form, the amount of force that Gwen feels would be equivalent to whatever her change in momentum is divided by the change in time. Now, what's her change in momentum? So what is this? This is what? Well, we have her final velocity. Final velocity is this. This is what the velocity that she's falling with when Spider-Man catches her. Now, Spider-Man wants to stop her, so this goes from 42 meters per second to 0 meters per second. That's my change in velocity. Now, her mass, Gwen, based on the comic books and what I've read about Gwen has a mass of approximately 50 kilograms. Okay. So our change in momentum will be her mass times her change in velocity. And her change in velocity is going from 42 to 0. So her change in velocity will be 50 times 42, which is, so 50 times 42. So her momentum, her impulse is 2,100. Okay, so 2,100. That's her change in momentum. And this will be in kilogram meters per second. Okay. So now we know how much her momentum changes by. So let's calculate the amount of force needed to change her momentum in a very short amount of time, of 0.2 seconds. So when you calculate this, the amount of force that exerted on her, so the 2,100 divided by zero point 0.2, she feels a force of approximately 10,500 kilogram meters, which we know is just, kilogram meters per second squared, which is just 10,500 newtons. So she feels quite a lot of force. Quite a lot of force. Okay. Now, the actual, the amount of force that, I guess, her vertebrae can experience before breaking is quite a bit less than this. Quite a bit less than this. I think depending on what you read, it's anywhere from between 3 and 4,000 newtons you can feel, and before your vertebrae break. So her vertebrae is experiencing a force of about 10,000 newtons, and it's no wonder that when we go back, let's go back. There it is. The comic book writers I don't know if they were actually cognizant of this, but they did put it in there that her neck snaps. And it's understandable considering just how much force Gwen felt when she fell and Spider-Man caught her and stopped her pretty instantaneously. Okay, now let's suppose that Spider-Man was a little smarter, and he's supposed to be because he's a pretty smart guy usually. Let's suppose Spider-Man stopped her in a much longer amount of time. Okay, so let's say Spider-Man stopped her, and it wasn't 0.2 seconds. Let's change it to let's say a full second. Okay, let's say full second. So full 1.0 seconds. So 1.0 seconds. Okay, in this case, then she would only feel a force of about 2,100 newtons, which is survivable based on the stuff that I've read. Okay, it is survivable she might have whiplash, but she wouldn't be dead. And all it would have taken was if Spider-Man just stopped her in a slower amount of time. Okay, and the difference between 0.02 and 1 second might not seem all that much, but when deciding how much force is acting on you, can mean the difference between life and death. Okay, and then this is the basic principle behind why we put padding on things, is because what the padding does, especially for things like helmets or airbags, basically anything that would experience collisions, you pretty much put padding so that you can increase the amount of time it takes to stop your object. And by doing that, even changing it just by 0.8 seconds changes the amount of force quite a bit. In this case, it changed it from 10,500 newtons to just 2,100 newtons. Okay, there you go. So that's kind of neat example, and also why we have padding in a lot of things. So if you're ever stopping something, don't stop too quickly, otherwise the things will experience quite a lot of force. Okay, we'll go through more examples like this later on. All right, now going off of that, one thing that Newton observed when dealing with momentum is that momentum tends to be conserved, assuming a closed system and you don't have loss of energy due to other things. Okay. Now, obviously, a closed system is kind of like ideal and doesn't always happen, but we can get some cases where it's mostly closed. And the calculations are quite, how can I put it? Not all that difficult, or not all that far off if you could assume things are closed systems. Anyways, in a closed system, the total momentum must remain the same at all instances, so that the total momentum is always constant. Another way to think about it is that the change in momentum is always going to be equal to 0. So if you have two objects colliding, the total change in momentum is going to be 0. So basically, if one object has a positive momentum change, then the other object will have a negative momentum change. Okay. This is quite important in a lot of collision analysis, and we use this a lot in things ranging from accident I guess, motor vehicle accident analysis to even things like nuclear physics. When we break apart atoms, we use conservation of momentum. Okay. But the main idea is that your total momentum remains constant, or you think of it as all changes in momentum are equivalent to zero. So once you add up the change in momentum from one object and you add it to the change in momentum of another object, then it ends up still being zero. Okay. So here's an example of this. So let's say we have a bullet. We fire it. It has a muzzle velocity of 600 meters per second. The shooter and the rifle have a mass of 60 kilograms. How much velocity will they recoil with? Well, remembering that our total momentum is constant, okay, or we consider that or change in momentum is equal to zero. So let's look at this. Well, the bullet, when it fires, when it leaves with a velocity, its momentum goes from zero to this number, to the product of these numbers. So its change in momentum is going to be 0.06 times 600 in some direction. So this is going to be, let's see, 3600. This is the momentum. This is the momentum that kilogram meter per second. So this is the momentum of the bullet. The bullet gains this much momentum. Okay, which means then the shooter and the rifle must have the same momentum, but they will be going in opposite directions. Okay. So the shooter and the rifle will have a similar change in momentum of 36 kilogram meters per second. But they'll be going in the opposite direction of the bullet. So when we calculate this, this will just be mass times velocity equals 36. The mass of our shooter is 60, or the shooter and the rifle, 36. So our velocity will then just be 36 divided by 60, which will be 0.6, I believe, meters per second. Okay, and then your assignment for today then is as follows. So just complete the 3.2 exercises on page 68-69, numbers 2 to 13. Okay. We'll continue our discussions, I guess, and study of momentum on Friday. And yeah, if you guys need any help, you guys know where to find me.